Okay, hello everyone. I'd like to thank the organizers for this opportunity to speak. I already joined last year and I'm glad to be back, although I'm still online. Unfortunately, I didn't have the, the freedom or like I was taken up by other things, so I can't travel at the moment. Um, so yes, I'm trying to, yeah, hopefully that didn't mess things up too much. Today I'll be speaking about a work that's on the archive. The archive link is at the end, about relative homological algebra, so something that Peter mentioned in his talk. This is a group work with some people from the TDA group at KTH in Stockholm, Sweden. So Wojtek Chacholski, Andrea Guidolin, Martina Scolamiero, and Francesca Tombari. And Francesca should be in the room. So if you have any questions, you can email me, and maybe I'm also setting up Francesca here. Maybe she can answer some questions as well. Yes, so let's proceed. So this talk will be about multi-parameter persistence. Something that has been observed and said today as well is that we do not have some sort of barcode decomposition or some sort of simple decomposition theorem for multi-parameter persistence. And instead, our approach is to approximate persistence modules by relative projective resolutions. And then we want to compute these. So we compute these, or parts of these resolutions, which we call Betti diagrams, using Koszul complexes, which are some mathematical tool. So first, before going to relative homological algebra, I want to speak about standard homological algebra, because that's where Koszul complexes can also be used in a simpler setting. So as for the previous talks, we'll be considering persistence modules as functors from an indexing poset to the category of finite dimensional vector spaces over a field K. So we denote this by fun I vect. And a simple example of a functor over a poset is a free functor. For an element A in the poset I, we can define the free functor at A as the following functor, which again has also been more or less defined in the previous talks, but with a different notation. So K A infinity, which point-wise is equal to K, the one-dimensional vector space, if B is greater than A and 0 otherwise, and then identity transition maps where possible. As a visual example, I will be looking a lot at this poset, the grid n squared, or maybe some finite grid, usually like a 6x6 grid here. So here in color are the points where we have a space of dimension 1, and then where it's not colored, we have dimension 0, and then identity maps between the colored parts. So this will be useful, at least hopefully, for some intuition. Once we have free resolutions, once we have free functors, we can talk about free resolutions. A free resolution of a functor is an exact sequence, m, f0, f1, and so on, where for all d greater or equal to 0, fd is a direct sum of these free functors at elements of the poset. And here I've represented this as a direct sum where each term has a multiplicity, and this multiplicity has a somewhat complicated notation, and this is because we will be looking at these afterwards. The free resolution is not unique, but there is a notion of a unique minimal free resolution. So for some definition of minimality, which I won't get into here, but in general, it's smaller, and hopefully the idea is that it captures some information about M. In fact, maybe all the information about M in a more encodable fashion. As an example, using this the example poset n squared, we can look at this poset, sorry, this functor on the right, the sort of small L shape here, and its free resolution, which looks like this. So we have one generator, so we have one element in F0, and then we have three relations. So there are three free functors at three different elements in F1, and then some relations between the relations in order to get an exact sequence. Okay. Going back to the Betti diagram, sorry, going back to the free resolutions, I've just written here more explicitly what the free resolution looks like. So we have M still, and then the FDs, they're direct sums. And here, let's say that this is the minimal free resolution. Then we want to look at these multiplicities beta 0, beta 1, and so on. We collect these by degree. So for a given d greater or equal to 0, we define this function beta dm, which for each element of the poset I gives the multiplicity of the free functor at that element. So this is the Betti diagram of M. And in general, so these Betti diagrams are nice because they're just numbers. So you can perhaps compute them and then input them into some classification or maybe some sort of machine learning thing. And also it's just a way to describe your functor more succinctly. However, in general, to get these Betti diagrams, or at least the first approach would be to compute the entire minimal resolution, which can be done algorithmically, but it is relatively complex. And in particular, the maps, these boundary maps or differential maps between the FDs are difficult to compute. And when we're computing Betti diagrams, we don't actually care about these differential maps. We just want the multiplicities of the free functors. So in a certain rather general setting, we can compute these Betti diagrams in a simpler way. So using something called the Koszul complex. So we need to assume that, or we don't need to, but one place where it works is when I is an upper semilattice. So that means that for any two elements of I, there is a smallest greater element, a join. And then for a functor M, an element A in the poset I, the Koszul complex of M at A is a chain complex of vector spaces, which looks like this. So we start out on the right with M of A. Then we have the direct sum of the M of B's, where the B's are covers of A. So these are elements that are smaller than A, but just smaller, just before it. So there's nothing between B and A in I, the poset. And then we have for any two covers of A, if the meet, so this is the largest smaller element, exists, then we take M at B wedge C. So all of these direct sums are just direct sums of vector spaces. There's a more formal definition here. So KAMD, so the dth term of this chain complex is you take D covers of A with a lower bound, and then you evaluate M at that lower bound, sorry, at the meet. And the differential maps come from the transition maps of M, or structured maps, as Jerry said, called them. I mean, there's lots of names for it, but so this is a chain complex that can be defined relatively easily from your functor. And the results, which was proven by some of my colleagues, or former colleagues, I guess, so Wojtek, Alvin, Jin, and Francesca, is that we obtain the Betti diagrams from the Koszul complex in the following way. The dth Betti diagram of M at A is equal to the dimension of the dth homology of the Koszul complex of M at A. So it doesn't necessarily look like one side is simpler than the other. Actually, the right side maybe looks a bit more complicated. But I want to point out that M is a functor over an entire poset. So depending on how you encode this, it might be very complicated. On the right side, we have a chain complex that depends on local information. So information about M at A and then some of its covers. And this chain complex is the chain complex of vector spaces as opposed to some exact sequence of functors. So it actually does simplify things, I guess. Yeah. Sorry. Okay. I don't have anything more to say, but I'll just keep this on the screen for a bit longer. We'll now move on to relative homological algebra. So I mentioned in the beginning that in multi-parameter persistence, we don't have a barcode decomposition, but we can try approximating functors by bars. So instead of having free resolutions, let's try having some resolutions of direct sums of other simple functors. So in the case on a grid, we can think of, for example, rectangles. Maybe that's a good generalization of bars. You can also see a bar as a free module quotiented by free functor quotiented by a free functor. So in higher dimensions or in general, we would have a lower hook. This terminology at least was introduced by Magnus Botnan, Stefan Opperman, and Steve Udo in a paper published 2022. Or we can look at something maybe a bit more general with one generator and several relations, like the single source spread modules introduced by Benjamin Blanchet, Thomas Brusle, and Eric Hansen, also in a paper published in 2022. I have some references at the end, including these ones. So we won't be able to do relative homological algebra or homological algebra relative to just any set of simple functors. So we want to control these in a certain way. And to do this, we introduce another poset, J, and we will parameterize the collection of functors of interest by J. And we do this by another functor which we call T, or we call a parametrization functor, which to every element of J associates a functor indexed by I. So yeah, then we are interested in homological algebra relative to these T of A. And for technical reasons that I won't really get into, T of A might be equal to 0. So we look at P, which is all of the non-zero elements in the image of T. Another important condition on T is thinness. We say that T is thin if for all elements A and B and J, the space of morphisms from TA to TB, remember that T and TB are functors, so morphisms are natural transformations, hence nat. The space is of dimension at most 1. So this means that there's not too many ways to go from one functor to another. In this situation, the general notion of relative projective resolutions becomes a bit more concrete. I haven't really defined what relative projective resolutions are, but they look like this. So they're sequences of the form M and then some other functors. And when T is thin, we have direct sums. So here the P is because they're relative to P because P is the collection of elements that are in here. So we have direct sum T of A, and then some multiplicity, and then direct sum T of B and some multiplicities. And again, I've used some more complicated notation for these multiplicities because these are these relative Betti diagrams that we will be looking at. So the relative Betti diagram here, beta PD, takes an element of J and gives the multiplicity of T of that element of J in the dth term of this resolution. Some examples of relative projective resolutions using the same original functor that we looked at before. So first example is rectangles. If we want to resolve this by rectangles, we take minimally, we take this rectangle, which is the smallest that covers our L shape, and then we cut out what's remaining. So that's just the kernel. For lower hooks, we have something a bit more complicated. So this lower sequence is for lower hooks. The reason that this might not be the intuitive, there's like simpler ways, there's simpler morphisms of lower hooks whose co-kernel is this functor, but those are not exact relative to lower hooks. So this exactness is not the original exactness, but I won't get into that. And the third example I had, these single source spread modules, I haven't shown the resolution because it's just the functor itself. It's already a single source spread module, so the resolution is of length 0. Okay, so I've introduced these relative Betti diagrams for these relative projective resolutions. And I said before that you can compute standard Betti diagrams. So now we want to compute the relative Betti diagrams. To do this, we will convert our functor m into a functor indexed by j. So like this. So for every element a of j, we associate the vector space of natural transformations from TA to m. And then the transition maps are naturally induced. Remember, so if you're concerned about the transition maps, remember that T is from J opposite to functors indexed by I. So if we go from A to B, we have the appropriate functor, the appropriate linear map on the right. So we have this nat Tm, and we will compute the standard Betti diagrams using Koszul complexes as described previously, and then transfer these diagrams to the relative resolution and the relative Betti diagrams directly using the main results. So this is the result of the preprint. So before we had I in upper semilattice, now we need J to be an upper semilattice, and then T is a thin parametrization. There's some other technical conditions, but these are all realizable, and in fact, they all work for the examples that I've given: rectangles, lower hooks, single source spread modules. And then we have the following equality again. So on the left, we have the relative Betti diagram of M at A, and on the right, we have the dimension of the d-th homology of the Koszul complex of nat Tm, so this replaces M, at A. Once again, we just have a chain complex of vector spaces on the right, so it's simpler than computing an entire resolution, minimal relative resolution on the left. I wanted to go through an example, maybe with some implementation, because there is a specific example that is more interesting than the others. So the lower hooks. The reason is that the relative exact structure for lower hooks is something called rank exact. So it preserves extra properties about persistence modules. So it's of interest. Also, it's also the simplest relative setting that is not the standard setting, because we will be using as a poset J just 2 copies of I, so pairs UV, where U is less or equal to V, with a product order induced by I. And our parametrization takes a pair UV and gives the co-kernel. So it's the co-kernel of it's the quotient of the free module at U by the free module at V. Another reason it's nice to work with lower hooks is that when we do this transformation of M into nat Tm, we actually just need to compute kernels. So we have an explicit description of this other functor that we are looking at. So then as I described before, we compute all of these kernels and put this into create a persistence module or functor indexed by j. Then we compute the Koszul complexes with this poset j, and we get the Betti numbers, the Betti diagrams, and we bring this back and report it as the relative Betti diagrams of M, relative to lower hooks. So I wrote some proof of concept code that it's just Python, so it's not super fast, but it's nice for some visual aids. So the input for the code is either a free presentation, or you can do more generally a presentation by upset modules. So I believe Jerry mentioned down closed sets. So this is the opposite. We have up closed sets. So these are functors whose support is an upset, and at each point in the support it's dimension 1, and you have identity maps when possible. The code is in F2, and we get something that looks like this. So the black dots represent generators in this grid, which is 100 by 100. The white dots represent relations, and the lines represent the boundary matrix, so defining the functor M. And in blue is the generators, and in pink is the relations. And then on the right, we have the Betti diagram, so beta 0, beta 1, and beta 2, represented by black lines. So a black line between 2 points of this grid means that the element of J, which is a pair of points, the lower hook associated to that has a Betti number that is non-zero. I don't really distinguish between multiplicity 1 or 2 or so on, but it already gives you an idea. And then I don't know if you can see, perhaps there are these dotted lines which are just the Betti numbers, Betti diagram of the previous degree, because there are sometimes interactions between them, and so it's interesting to look at that. I've been talking about things being easier or harder than others, so here's some complexities. These are just initial estimates. They're not super optimized. So the estimate for the Koszul complex code is some exponential in the dimension of the grid, and then n to the 2r plus 3, where r is the dimension of the grid. The implementation is only r equals 2, so it's n to the 7th. And n is the number of generators and relations in the input presentation. As a comparison, as I mentioned, the naive approach would be to just compute entire minimal resolution. If I did my computations correctly, it should be something like, if you ignore the r, because most implementations will probably be r constant, it's n to the 8r, which is much greater. And then another invariant that is very related from the Botnan, Opperman, Udo paper is the sign barcode. And based on discussions with Steve, I'm pretty sure the complexity is something like n to the 2r plus 1. So it's faster, but it also has slightly less information. So I think that makes sense. As a summary, we have 2 posets. We have a poset I, where our functor lives, and then a relative poset where the simple functors live, essentially, or how they're parametrized. And then we have a correspondence between these two, between M and NatTM, copies of TA and copies of KA, where A is an element of J. And then these Koszul complexes, which compute multiplicities in both the relative minimal resolution in the absolute poset and the standard minimal resolution in the relative poset. There are some results on stability already, not necessarily directly about the Betti numbers, but the alternating sums of them, which Peter mentioned, there's a paper or a preprint, I guess, by Botnan, Operen, Udo, and Skokula that says that they aren't too stable. And so one future work would be to stabilize these with a method called hierarchical stabilization. And then this would give new computable metrics for functors that are stable, which would be nice for alternative ways of analyzing data. And yeah, that concludes my talk. Thank you for your attention. Here are some references and then the preprint.
Questions?
Yeah, very nice job, Ben. Can you say a bit more about the parametrization functor J? So, like for the lower hooks, for example, would those be the objects in that category J? And then morphisms would be conclusions of lower hooks. Am I thinking about it right?
So it's almost that. So we take J to be a poset that you define, usually it's defined based on I. So first of all, it's a poset. So it's not like an arbitrary category, but given the constraint of thinness, there's actually quite similar. So I don't know if maybe this slide is better. In our case, yeah, and so the morphism of this functor, so if we have A less than B in J, then we'd have a morphism from T of B to T of A because we have this opposite. And for lower hooks, that would just mean that because the order for lower hooks is the product order, is we have a lower hook whose generator and relation are greater than respectively the generator and relation at the target. So it's not really inclusion, but it's just the existence of a morphism.
I see. So this is an extension of the idea for intervals in the one parameter case, right?
Yes.
Thank you.
Any other question?
There's one on the chat.
So GN Liu asks, like, so all the persistence module considered are finitely generated?
Yes. So in the setting, so there are more general settings where this theory should work, slightly adapted. But for our setting, we're considering, I think there's supposed to be a finiteness hypothesis at some point, maybe not at the right beginning, but so the posets are finite and the vector spaces are all of finite dimension. So all the persistence modules are finitely generated. Yeah.
There is one more question from the audience. You have to speak a little louder.
Yeah, why do we work over field K? Why not R module?
That's a good question. I think for now it's just for computation reasons. I believe, yeah, there's a lot of matrix reduction that goes on behind the scenes. So it's nice to work with invertible elements. And yeah, and in fact, at least for the implementation, working with F2 makes it even simpler too.
Do you think
Yeah, so it's
that it'll carry through to our module? So these other constructions seem to work in a more general case.
I mean, yeah, I don't have anything off the top of my head. Yeah, other than like general, maybe it's just a belief that fields are better in implementations. It's more implementation oriented.
Any other questions?
So, is there any relations with the fit of the Koszul homology and the RF computing numbers? the
I didn't quite catch the question. Is it about a relation between?
the homology and this homology is the Koszul homology.
Yes.
Yeah, okay.
Okay, so let's thank all the speakers in the morning.